this is going to be a cool lecture. We're in our second lecture on magmas. So this is Magmas number 2. And what we're going to do today is a topic called Magmagenesis. How do we actually melt rock to make a magma in the first place? And I'm going to tell you that there's 3 ways to do it. And before we get to it, we have to introduce 2 important words. We're going to do it in the form of this graph. And the graph drawing today is important. And what this is a view into the subsurface where we have temperature in Celsius. There's like 500 degrees Celsius. Maybe here is 1,000 degrees Celsius. And on this axis, we're going to do pressure, or we could also say this is depth. Right? And the idea is that as we go deeper into the Earth's interior, temperature rises. And to show that as a line would be something like this. And we call that line the geotherm. Hotter with depth. That's what geotherm means. And we can put that as a definition if you need to. Let's say hotter with depth. Maybe a textbook would say heat is stratified within the Earth's interior, and we go hotter with depth. Anyways, great. Now we're going to put in a second line on this graph. And this line is called the solidus. I'm going to label it. And solidus is a fancy word in petrology, the study of rocks, that means the freezing or melting of a rock. Freezing or melting of a rock, right? So if you're on the hotter side of the solidus, there is melt. And if you are on the colder side of the solidus, there is rock. And the key observation here, we could put a star. The key observation is that under no conditions, normal conditions in the Earth's interior, is the geotherm create an environment that's hotter than the solidus. Therefore, the Earth's interior is too cold to melt. Right? The geotherm is colder than the solidus. Everything has to be rock. But we know magma exists, so there has to be circumstances, special ways to make this not valid. But we're going to say as a general comment, under normal conditions, the Earth's interior is too cold to melt. And now, for the rest of the lecture, let me talk to you about the 3 special ways that we can allow melting to occur. I'm not going to insert any pictures today. Today is only going to be drawing. And with each of our drawings, we're going to have that same line of the solidus and the geotherm with respect to temperature and pressure. And so for our very first mechanism, I'm going to give it a symbology that we're going to label as plus T, which means adding of temperature. And the official name for this mechanism is underplating. Underplating. And the idea with underplating is that we bake the overlying material. Okay, so this means we're going to bake overlying material. There's some magma that is already existing and it intrudes up into the crust and it melts rock above it. So this cannot be the original source of melting, but it is definitely a way of melting. So here's our graph of temperature and pressure. And we have our geotherm, and we have our normal solidus, and the 2 do not cross. But now with red ink, I'm going to tell you what happens when we add magma underneath this environment. We actually change the position of the solidus until, right, and we could draw little arrows. Whoa, the area is getting hotter, the area is getting hotter. The position of the geotherm now crosses the solidus, and so melting can occur. All right, so let's label these things. This is our geotherm, and this is our solidus, and in red is our new geotherm because of this baking phenomenon. Where do we see this kind of thing? Well, actually, it's possible at all tectonic environments because it's not a primary melt. This is a secondary melt. Primary at all tectonic environments. Okay, no, I think that's the easiest one of these to understand. The next, we're going to give the symbology of minus P, and what minus P is means drop in pressure. Underplating was increase in temperature, we're baking. Minus P means decompression, and I'll show you on a graph how decompression can actually change a rock and allow it to cross the solidus and melt. And so what we'll do is we'll draw our graph again. I would recommend strongly that you can do this on an exam. Here is temperature, and here is pressure, and the geotherm is here, and our normal solidus is here. And what decompression does is we take mantle that is hot and we actually rise it by motion. So things as they're rising up, what am I trying to say? We change the position of the geotherm. And things are hotter than they should be, creating an environment for melting. All right, so let's see if I can explain that now with words, as like, what do those arrows mean? Well, the best example is rising mantle. And so what we're gonna say is rising mantle in some tectonic environments keeps its heat. The interior of the earth is well insulated, and mantle is viscous, so it can move, and it can move faster than heat can be lost. So rising mantle stays hotter than it should be, okay? Rising mantle keeps its heat and moves the geotherm hotter. Moves the geotherm hotter. And so that, moving the geotherm hotter, are these red arrows right here. The tectonic environments where this can occur is at the mid-ocean ridge system. And then also at hotspots. I'll make a quick sketch of each of these, and then you can confirm this later by like reading the textbook. But at the mid-ocean ridge system, right, we have two lithospheric plates that are pulling away from one another. And as they're pulling away from one another, mantle rises up to fill that gap. And as that mantle rises up to fill the gap, we get to a place where melting can occur. And so at the mid-ocean ridges, like a place like Iceland, there is significant magma and volcanism. The other environment is the hotspot rise in a mantle. And so the example here is, let's imagine we have Hawaii, and we know Hawaii are these volcanic islands, right? And they are sitting in the ocean, and only the tips of them are sticking out. Well, why is there magma forming? Well, because the mantle at the hotspot is rising. It's maintaining its heat, and it causes the mantle to melt in blips until magmas are produced, which then can erupt. All right, there's our two easiest mechanisms for melting. And this third one is a little bit unusual, and we're gonna give it a symbology of plus H2O. So for number 3, our symbology is plus H2O because water matters here. And I don't even have a good name for this one. Eventually we're just gonna call this subducting water. Melts mantle. That's not a great name, but it's long, but it is accurate. So here is the story for the plus H2O mechanism that occurs at subduction zones. We have our geotherm and we have our solidus. And here's what water does. Water changes the actual position of the solidus. This is, in all the other ones, it was the geotherm that moved, but in the subduction zone, the geotherm stays the same, and as you add water, the solidus changes. So we're actually moving the line this way. And if you add enough water, we get that situation where there's a crossover and there is an opportunity to make magma. Now, the amount of water to do this is actually very small. It's about 0.1 weight percent H2O. And subducting slabs are made up of clays and water in porosity and other minerals that have water. And so getting that 0.1 weight percent H2O isn't too hard. All right, so that's our drawing. We're gonna say addition of small amounts of water changes the slope of the solidus to allow colder melting. Let's make sure we see that in the graph. So addition of small amounts of water, like 0.1, changes the slope of the solidus, right? So here it's a slope with this direction. Now we've changed it so it goes backwards, and it allows colder melting. Sure it does, because here is pressure and here is temperature, and now the solidus has actually shifted down by, I don't know, 200 degrees Celsius. That number we would need to look up, but it can be a big change. The geology of this process, this occurs at subduction zones. I guess we could try to give this a sketch as we finish off this lecture. So as a subduction zone occurs, what do we have? We have our subducting plate going down below our overriding continental plate, and this is always drawn with a trench, and the trench, like the Marianas Trench, is the deepest place. And what I want to have you see, here's what we're going to draw. We're going to draw some little squiggles of water coming off this plate. And the reason for that is there's too much pressure. Water is released from subducting slab. And as that water gets into the mantle, we call it the mantle wedge, it'll make a little bit of melting, which can then make magma chambers occur in the crust, which then can lead to volcanic eruptions like Mount St. Helens or Mount Fuji. That's the kind of melting that occurs in those locations. So this is part of the why. Part of the why. So this is the why. Does it occur? Well, because the water is released from the subducting slab. But the other aspect of the why is that water weakens bonds. And by the addition of water weakening bonds in a mineral, it allows easier melting. So let's say H2O weakens bonds in minerals, which allows easier melting. And to leave you with one last thing, right? If this is kind of like racking your brain, in the north of the United States, we get a lot of snow and ice. What do you put down on that snow and ice in order to be safe on the roads and on sidewalks? You put down salt. And so our comparison, it's a really good one, is salt plus ice. And for every 1% of salt you add, you actually allow water to exist at colder temperatures. So let's say 1% salt allows water to exist at 1 Celsius colder. We have changed the freezing temperature of water by adding something to it. That is how this plus H2O magmagenesis occurs at subduction zones.